So please give me a warm welcome for Jianmin Wang, exploring two applications in China. Take it away.
Thank you very much. Good afternoon, dear friends. I'm Jianmin Wang from Tsinghua University. You may have experienced and heard about the use cases of Cassandras in US or other places. Today, I'm pleased to introduce the two exemplary Cassandra applications in China in the opposite side of the Pacific. My talk consists two parts. First, who we are. We are from the Institute for Data Science, Tsinghua University, which was founded in April last year. Our missions include recruiting world-class researchers and engineers in industry and academia, long-term dedication to system research and industry practice. The third is leading China's big data strategy, especially for industrial big data. Nowadays, a lot of people are talking about big data. Where the big data comes from? Firstly, data generated by people, especially on internet. Secondly, from the online scenario, such as internet, to the offline scenario. In the real world, machines are generated even more data than people do, such as data from equipment, sensors, RFID, etc. Thirdly, tons of semi-structured software log are generated by computers. Let's look at the workload of machine-generated data. They exist broadly in several industries, such as agriculture, utility, industrial business. Machine data is always formatted as time series with device identifier, timestamp, and value. Or irregular interval as temporal sequence, or adding GPS attribute to each record. Different from other structured data, like transactional data in CRM. Machine-generated data is about 24 hours a day and 7 days a week continuous stream. And in a single application, its volume can easily reach 1 billion records per second by either high-frequency sensors or millions of sensors. The machine data need to be processed and persistent in real time. And more important, data will be also used for complex query and analytics, such as based on the content, their shapes, and the spectrum. We talk about machine data three ways, but it's not just volume, velocity, and variety. Take industrial business, for example, as an emerging of several new trends, like industrial internet from US, Industry 4.0 from Germany. People realized the importance of the industrial big data, which they really have. But the real challenge comes from how to generate value from these data, rather than just process and store the data. In our viewpoint, the big data in industrial business is more than technology. The answer to this question is how to get line of business involved easily, proactively, and deeply. Let's look at the big data lifecycle of machine-generated big data. We need the infrastructure to store the data, support concurrent and complex query in the first step. Also, we need to process the data, to clean it, and receive it into a proper size and granularity. At step 3 and 4, the data are ready for access, exploration, modeling, and analytics. Today, we will focus our work especially on data storage with Cassandra. Now, let's look at the industry sensor data management with Cassandra in China's Sany company first. As you know, China is a big industrial manufacturing country. Sany company is a global company in the construction machinery industry, which is relatively similar with the Caterpillar in US, I think. There are more than 200,000 active heavy machinery, which are made by Sany in more than 150 countries. Currently, we do not only care about the manufacturing process, but also care about the after-sales services for these smart products. For example, we want to report the working status of these machineries. We also want to forecast the part fault before it appears and to improve our products by analyzing the historical data records. To do that, we need to collect and store the data as much as possible. There are many sensors embedded in the machine today, made in Sany Group. When the machines are working on the construction place, the sensors collect data and transfer them to Sany data center by 3G or GSM internet. Nowadays, these are located in the Changsha city. The data records the running status of machines. For example, when the machine is traveling, we collect their speed, their location, and the fuel load. When the machine is working, we collect the chassis angle, the pump pressure, and so on. Currently, Sany has more than 5,000 kinds of sensors, and the machine will produce more than 50 billion records per year. Sany Group began to manage their sensor data from 2008. Along with the increment of data, Sany Group released the SQL Server with Oracle. But it's not enough. In 2012, a table in Oracle stores tens of billion records. It will spend several 10 minutes if a DBA run a SQL with where clauses. As a result, Sany only put 6 months data into Oracle and dumped the older data offline. From then, we try to help Sany to replace Oracle with Cassandra. At that time, we use Cassandra version 1.20, a very early version of Cassandra. We analyze the characteristics of the sensor data, design case-based and column family schemas, and experimentally import data and test the system performance. This process lasts 2 years. In 2014, the new system with Cassandra began to replace Oracle in production system. Now it works well, I think. This is our software stack. We use Storm to handle the sensor data first, and then write them into Cassandra. We also developed some applications to analyze the data with the MapReduce framework of Cassandra. In Cassandra, we design each sensor to a column family. Therefore, we have more than 5,000 column family in total in one case base. You can see for each column family, we use machine date as a row key, use the gather timestamp as a column name, and store the sensor value as a column value. The reason for our schema design has two facets. The first, the Cassandra system before version 2 does not support multiple primary key or clustering key. It means the key just for a single attribute. Another reason is the advantage to store each column family or say a sensor in a single column. It is a similar design of column store to avoid unnecessary access to the other data, since most of access sensor data in Sany application are against a single sensor. I think it is a very traditional sensor data management application. However, there are also some challenges. The first is creating schema hand. You may think it's very simple. In our case, we need to create more than 5,000 columns in batch. When we create column family SQL statements, we find it spends too much time. At first, each SQL statement spends less than 1 second. After we create about 300 column family, the time cost for each increased to 10 seconds. At last, for the single statement for create column family, we'll spend more than 20 minutes. What's the reason? We monitor the memory cost and find at this time, Cassandra uses a lot of memory. Finally, we find the reason. When one server, just the coordinator, receives create column family request, it will propagate it to other nodes. Meanwhile, gossip protocol will find the schema on each node is different. Then it will try to synchronize the incomplete schema modification frequently. The left top figure shows the original gossip protocol. Both the gossip protocol and the message propagation can find the schema inconsistency and initialize a carry-up. After analyze the reason, we do some modification to let the gossip take effect only in 2 cases. The first is when a node does not receive a propagate message. The second is when a node recovers from a failure. In this way, we can make the column family creation time cost to be almost consistent. The second challenge is data inconsistency. We know Cassandra applies eventually consistent model. So inconsistency exists in the system. When we import data into Cassandra in a very high speed continuously, when we set the right consistent level with 1 and the replica number is 2, is not many, and the cluster has 5 nodes. After loading 30 billion records, we stop the load process and try to check whether the data is consistency. We find that a same select command on different servers, the results differ. After finishing a repair operation, even after finishing the repair operation, each server increased 25 volume of data. It means that only 75% data is written successfully in one replica. Why the repair process doesn't work on this situation? Because for each range and each column, Cassandra needs to create a Merkle tree and transfer it to other node to compare the replica consistency. So in this scenario, there is too many column family and too many data range. So Cassandra repair process takes a long time and not very effective. The third challenge is the heterogeneous node. Our experiment shows that when we add 8 PC servers into existing too powerful server cluster, the overall cluster performance comes even worse, even though we change the data partition according the node capacities. The cluster performance does not improve ideally. The root cause is the mechanism of replication, which means the node is not only responsible for its own data range, but also need to take care of its neighbors. Once a strong server sends the replica request to a weak server, it needs to wait for its response. When the read consistency is in the quarter level, it means that the powerful node has to be idle until the busy weak node completes its job. In this slide, if the node file is a strong node, it will wait for the weaker server node 1. Another issue is how to allocate the number of virtual nodes. Certainly, the bigger number of virtual nodes we have, the more space we can optimize the location of virtual node But Cassandra has its upper limit for the virtual node. On the other side, the number of virtual nodes can lead to the overhead on the lookup table. Our solution is to combine the position and the range for optimization together. We have published 2 research papers to solve this challenge with a quadric optimization model for cluster initialization and a dynamic programming approach to search for the best position when a new server comes in. After overcoming the previous challenges, the Sany Group upgrades their sensor data management platform to Cassandra successfully. Nowadays, they can put their 3 years data online with the Cassandra platform. From the Sany application, we learn more requirements for the industrial big data platform. The first one is more than 1 or even 10 million data points per second are very common in this area. The second is we should reply the complex time series query within 1 second. The third, we should synchronize the edge data processing with the cloud end data processing. The fourth is even more, the system should provide adaptive deep data comprehension capacity. Finally, we should execute the trajectory-based query efficiently. This is an industrial sensor data analytic pipeline in Sany. To generate the real value from data, we build several analytic applications together with Sany Group for their R&D, quality control, and their after-sale service divisions. This is our first exemplary application. Let us take a look at the example. This kind of machine requires stable support to pumping concrete, and thus the legs with cylinder are designed to prevent tip over. And these legs will adjust to supporting force according to signal from inclination angle sensor. In order to find out the reason, we collect online inclination angle data from more than 13,000 on service concrete pumps. Through the concrete correlation analysis, we find some reasons. The first is a highly unstable instance, which means this pump shakes widely while working. The second type is an idle instance, whose inclination angle sensor never changes. This means the sensor does not work. Based on such observation, we can drill down to investigate the individual concrete pump trunk who has the above situation. The second application is the fault diagnosis, where time series analysis and spatial correlation. We find the leakage problem of master cylinders is highly correlated with a high-speed rail construction project. The third application is the spare components demand forecasting. Combining the real-time data from machines, sales history, holdings of vehicles, environment data, even the GDP data in a different area, we can reduce half of the inactive spare part inventory. This is our application in Sany company. Now, let's come to the climate data management in Cassandra. There are 4 steps for processing the climate data. Firstly, collect the weather data. Most of them comes from the sensors or the machine-generated data. Secondly, transmit these data into cloud data center. Then, the end users, most of them are climate specialists, can access the data and produce the weather report. Now, let's see the characteristics of the climate data. Climate data is a hierarchical data. China Meteorological Administration uses 7 kinds of data to predict the weather. As you can see, such as the lightning data, ground data, aerological, and others such as satellite, radar, typhoon, and model data. Where model data are the most complicated one and produced by powerful server clusters. Each model data has 71 kinds of parameters. For example, T639, the China model data standard, has temperature, wind field, rainfall, snowfall, and so on. For each parameter, there are about 20 levels, which represents the weather condition in different altitudes. And for each level, there are many time points. Totally, there are 16.5 terabytes climate data stored in 2.8 million files per day. Users in China Meteorological Administration need to browse the climate data quickly. Therefore, they need a high-efficient data cache system to support the end user to get a data file within 50 milliseconds. For example, if user want to scan data in dimension order 3, which means along the altitude level in the right finger. If we organize the data file in a tree, we must travel in the tree structure along different levels. It's very time consuming. In this project, we choose Cassandra because its scalability and read-write efficiency. And because the column is sorted, we can organize the data in time order so that it is easy to scan the data in order along some dimension. We know Cassandra uses LS tree structure and will compact access tables into a new one. We also use Cassandra's new features about the time-based compaction, so we can delete the previous obsolete data easily. This is our schema. The climate data is a multi-dimension hierarchical data set. Some dimensions are ordered. We use them as a column. Some of them are not. We use them as column family row keys. We use a clustering key structure. You can see the final climate data are organized in the file space in the right fingers. The results. After 1 year implementation, the system in China Meteorological Administration is online, which is 100 times faster than the older system. This is the end of my talk. Thank you for your attention. Thank you very much.
Any questions for Jianmin? He's asking to go back one slide.
One slide? Okay.
He wants to take a photo. No question. Any other questions?
Is there any specific reason to maintain the replica 4 instead of 3? The replication factor, maintain it as 4. Is there any specific?
Sorry.
The replication
loudly?
factor. The replication number 4, is there any specific reason to maintain it as 4 instead of 3? Yeah.
Oh, yeah. Because this application is very mission critical, so they cannot afford losing of their data. So you use.
So it should be, odd number should be better, right? 3, 5 rather than 4.
Sorry?
I think this is a customer's requirement. In some cases, the customer is not that technical, deeply understanding. They just think you can increase the number of replicas. They think that is much safer for them.
Yeah, but I think even with the 4 or 3, right? So the node down scenario with the quorum is going to be same, right?
Yes, we know that.
Yes, there is a story, because the first they use the two replicas, and after a half year's operation, a node was destroyed. Yes. So after that, they choose the 4 numbers replicas because the machines is not very reliable, I think.
I have a question right here about challenge number 3 that you mentioned about heterogeneous nodes. You said that you use quadratic optimization to find the best positions of the virtual servers. Can you elaborate on that a little bit? Like the best in terms of what? Okay. Challenge 3.
Okay.
So it's way back, I think.
Challenge 3. Okay. Yes. Okay. How to? Sorry, cannot.
I think we'll have to take that one offline. Let's
Yes,
give our speaker.
we just.
Go ahead.
Yes, we just think, model this problem as optimization structure, and considering the replica and the replica position on the different node. And we just calculate a linear optimatic metric, yes, to solve this problem. Right. Right.
Let's give our speaker one last round of applause. Thank you very much.
Thank you.